Hello everybody. In this video we're going to be covering section 17.2, Galvanic Cells. We're going to describe the function of a galvanic cell and its components, and we're going to use cell notation to symbolize the composition and construction of galvanic cells. So the first thing I want to do is think about a reaction that we've actually seen before. In this reaction we have silver nitrate solution here. So it's in solution, so it appears clear. We have a copper coil. When we put the copper coil into the silver nitrate, what winds up happening is some of the copper comes out into the solution, and the silver that was inside of the solution starts to plate itself onto the copper and come out as a silver solid. So if we think about the overall reaction here, we have a copper solid that is going to an aqueous copper cation in solution, and we have silver cations that were in solution coming out as a silver solid onto the coil. We can break that down into two half reactions. We can think of it as two steps. There's the step where the copper solid went into solution, liberating two electrons, and there is a step where the silver that was in solution gained two electrons and became a solid. All right. You can notice that two electrons were transferred in this process, and what is implied here is that the electrons that the copper gave up were the same ones that the silver cations took on to become a solid. And you'll notice that this reaction created electrons, and that is therefore oxidation, because oxidation is loss of an electron. And this in this step it took on electrons, and that is reduction, because reduction is the gain of electrons. We also will note that the direct transfer of electrons from the copper wire to the aqueous silver ions is spontaneous. And we're going to see soon that that's not always going to be the case. It actually depends on the chemical nature of the two metals that we have in solution. So now that we've thought about that system as we just saw it, let's talk about what a galvanic cell is. So these are electrochemical cells, and they're devices that contain all the reactants and products of a redox system, like the one we just saw, but they prevent physical contact between the reactants. So rather than having the copper directly exposed to the silver nitrate, we're going to keep them separate from one another. This prevents the direct transfer of electrons from one of the species to another. Instead, what we're going to do is we're going to redirect those electrons through an external circuit, all right, that's going to be in contact with the two reactants. What that's going to allow us to do is that flow of electrons through that external circuit is electricity, and we're going to be able to do work with that electricity. Devices based on spontaneous redox reactions are called galvanic or voltaic cells. Okay, so they're spontaneously going to produce electricity. These galvanic cells are going to be comprised of two half cells. Okay, in each one of the half cells, a half reaction is going to take place. They each contain the redox conjugate pair couple of a single reactant. All right, meaning that, for instance, the one of them would contain both copper solid and the copper 2+ cations in solution. The other half cell would contain the silver and the silver solid in solution. The external circuit that we were talking about before is connected to each of the half cell at its solid electrode. All right. So the solids in this case are going to be the copper solid and the silver solid. The anode of an electrochemical cell is the electrode at which oxidation occurs. The cathode is the electrode where reduction occurs. Okay, so oxidation is loss of an electron. Reduction is the gain of an electron, which helps, which leads me to a phrase that I like to remember that helps me to keep this all straight, is that electrons are going to flow from the anode to the cathode. From the anode to the cathode. Now, we can't actually just separate it and just have the reaction take place, because ultimately we're going to create a circuit, meaning that we need to have it be a complete and total closed loop. All right. If you ever learn anything about circuits or anything like that in physics or in electronics, all circuits are loops. They always come back to where they started. All right. To keep the reactants separate while maintaining charge balance, the two half-cell solutions are connected by a tube filled with an inert electrolyte solution. We call this the salt bridge. The spontaneous reaction produces cations at the anode. So if we go back here at our anode right here, we're producing copper cations. And it's going to consume anodes at the cathode. Okay. A compensatory flow of inert ions from the salt bridge maintains that charge balance. All right. So now that we've gone through all of that, I think we're ready to take a look at the actual diagram here and see how this actually winds up working. Okay. You can start at any point, but I like to start over here with the anode. Okay. So what's happening is I have this copper solid and it's having this half cell reaction. Okay. Copper is coming off into solution and producing these copper 2 plus ions. Now, and liberating 2 electrons that are going to move up and into this wire. Now, if it was true that these copper 2 plus just kept going out into solution, then that means overall this solution would start to gain a positive charge. And that just doesn't happen. The physics doesn't allow for that. We've never seen that. We always have to have these counterbalancing anions. So to counterbalance those added copper 2 pluses there, we need to be able to add more ions, negative anions in to balance it. And that's where this salt bridge comes in. Okay, it contains sodium nitrate in this case. Nitrate anions are going to come down and they're going to be added to the solution at the same rate that these copper 2 pluses are to keep our balance in that solution. Now we can follow our electrons. We're going to come up here. It's going to move across this circuit. It does some useful work. It turns on lights and stuff for us. It comes over here and it comes to the silver cathode. Our reaction here is that silver is coming out of solution after the addition of the electrons it got from the copper, okay, and it's turning into silver solid. So now silver is coming out of this solution and it's being plated onto this silver cathode, okay. So while this copper anode is losing mass to the solution, the silver cathode is gaining mass from the solution. We would have a deficit of silver cations at that point, right? There would be too many anions in that solution. We need to replace that with sodium cations from our salt bridge to keep, again, the charge in the solution neutral. At that point, we have created an entire circuit to follow around, and we have separated the two reactions to create our galvanic cell. You'll notice that all of the negative charges are flowing clockwise around here. So those are our electrons. They're flowing clockwise around the system. All right. And our negative anion is also moving clockwise. All right. Now all of our positive charge carriers, the copper cations and our sodium cations and our silver cations, they're flowing the opposite direction. They're going counterclockwise across the circuit. All right. So it doesn't matter if we have negative charge carriers flowing clockwise or positive charge carriers flowing counterclockwise around the circuit. we still can close the loop ultimately and get electricity flowing through it. So cell notation or cell schematics are an abbreviated symbolism commonly used to represent galvanic cells by providing us the essential information on its composition and structure. We write them with a few guidelines. First, the relevant components of each half cell are represented by their chemical formulas or elemental symbols. Okay, so that's pretty straightforward. We're just kind of using the same sort of symbols and nomenclature that we've been doing for chemical reactions. All interfaces between component phases are represented by a vertical parallel line. Okay, so if I go from, say, the aqueous phase to the solid phase, I'm going to have a vertical line there. If two or more components are present in the same phase, their formulas are separated by commas. All right, so I have two different species, but they're in the same phase. Maybe they're both aqueous or they're both gases. I'm going to put a comma there instead of a vertical line. You're going to use a double vertical line to represent the salt bridge. And by convention, the schematic begins with the anode and proceeds left to right, identifying phases and interfaces encountered within the cell, ending with the cathode. So I go up from on the left-hand side, I'm going to have the anode. On the right-hand side, far right-hand side, I'm going to have the cathode. So let's do a little example here. A galvanic cell consists of solid copper anode. All right, so again, I'm starting with the anode. So I have copper solid there, immersed in an aqueous solution of copper 2 nitrate. So that copper anode is in contact with copper 2 nitrate. So those are different phases, solid and aqueous. So I put a vertical line, and then I note that I have the copper nitrate. Okay. That is connected via a salt bridge, double vertical line, to an aqueous silver nitrate solution. So I write my silver nitrate solution there, immersed in which is a silver cathode. So again, aqueous and solid, different phases. I put a vertical line and I note that I have the silver solid there, which is our cathode. We started at the anode, we ended at the cathode. Let's try a little bit of a trickier one now. A solid magnesium anode is immersed in an aqueous solution of magnesium chloride that is connected via a salt bridge to an aqueous solution containing a mixture of iron 3 chloride and iron 2 chloride, immersed in which is a platinum cathode. All right, so first thing I have here, solid magnesium anode. I know that at my anode, I'm going to be having an oxidation reaction, and I can see that that's going to magnesium chloride, right? So I know magnesium chloride contains magnesium 2 plus cations, so I can write my oxidation half reaction. I've got magnesium solid going to magnesium 2 plus cations. That's going to liberate 2 electrons. Now I says is connected via a salt bridge, meaning I'm moving away from my oxidation half cell towards my reduction half cell. An aqueous solution containing a mixture of iron 3 chloride and iron 2 chloride. Now I have to make a little bit of educated decision here. Okay. I know that I already did my oxidation half reaction, meaning I already produced electrons. I now need a reduction half reaction. I need a reaction where I'm going to be accepting electrons. All right. So if I have iron 3 and iron 2 and I wanted to accept electrons, well, I need to take the iron that has the higher oxidation state, my iron 3. I need to give it some electrons, and then that's going to give me my lower oxidation state, my iron 2. Okay. Now, in this step, I liberated 2 electrons. I need to accept 2 electrons down here. So I had to double each one of these components in order to get that charge balance, so that this is able to accept as many electrons as this reaction is giving off. I can then add those together and get the overall equation for this system. Now that I know that, it makes it a little easier for me to write out the whole cell reaction here. Okay, I'm starting at the anode. I know that I have a magnesium anode. I know that that is in a solution of magnesium chloride here. I know that I have a salt bridge. It's drawn here with sodium chloride. An important thing to note here is that so long as this is a very soluble salt, it does not matter what it is. Okay, you'll see sodium chloride is very popular, sodium nitrate is very popular, and if you think back to what we've learned about equilibrium and solubility, pretty much any sodium potassium type salt is going to be very soluble and be able to be used as a salt bridge. Then I have my reaction at the cathode over here. Now this is different than the other example we have because we have no solid now. Okay, we're seeing the reduction of two aqueous species. So there's no vertical line separating them. Instead, we have a comma because they're in the same phase. That would present us with a problem though, because where am I going to attach this lead over here, right? I need to have some sort of solid to attach that to. And that is why we introduced this platinum here, okay? The platinum is not participating in the reaction. The platinum is just a mechanical component that we can attach this lead to that's going to be able to conduct electrons down into the solution for this reduction reaction to occur. All right. So what we call that electrode that we've just added is an inert electrode, okay? And they are required when neither member of the half cell's redox couple can reasonably function as an electrode, meaning that they're not going to be any solid there for me to attach that lead to. They're they need to be electrically conductive and in a phase separate from the half cell solution.